Good morning, guys, once again. And welcome to this class. This is just a continuation of the previous class on vectors. So if you haven't watched the previous class on vectors, please go back and watch that before you start watching this, because this is just a continuation, which actually built up from where we ended in the previous class. So the last part we had looked at in the previous class was parallel vectors and equivectors. Yeah, we ended on parallel vectors and equivectors. That's where we ended. Now, I made mention that parallel vectors are just vectors that are multiples of each other. Yeah, so they are basically in the same direction or opposite direction. So you have this and that is parallel, or it may be in that way. All these are parallel. Okay, so that's about parallel vectors. So now today I am moving a bit and I want to talk about just mere addition and subtraction of vectors geometrically. So I just want to talk about addition and subtraction, subtraction of vectors geometrically. Now, when I say geometrically, I mean by way of sketch. So we want to add and subtract vectors using some sketches, using some diagrams. Okay, so let's say I'll start with this example here. So I'll start with this example. Let's say we have this sketch here. This point is B, this point is A, and this point is O. So let's say that is in that direction, and this is in this direction, and this is in that direction there. And I'm asked to find AB, which is a direction vector. From A to B, I'm moving from A to B. Now you see, A to B is in that direction. So we'll move that way. Now you can see that moving this way is in the opposite direction. I left out some information. This is A. This is given as A. This is given as B. Okay, so you can see that moving in this direction is in the opposite direction. So it will be negative A because we are going back in that direction. So for me to move from A to B, I have to follow this route. I move like that and I go that way. So this is negative, okay? That is positive because it's in the right direction. So you can see that the answer is going to be negative A plus B. That's what we're going to have. So we have negative A plus B. That's what we're going to have. Okay, which is the same as what? Which is the same as AO plus OB, right? So that's AB, okay? That's AB. That's AB. Okay, so let's look at the second example. The second example where we have A is actually a point. A is a point with coordinates. A is a point with coordinates 1, 0, 3. Those are the coordinates of A. And B, B also is another point with coordinates. B is also another point with coordinates 3, negative 2, 6. Okay, so the first question is find using column vectors. Find using column vectors. Find using column vectors. The first question is we're taught to find AB. That's the first question. And then the second question is we are taught to find a position vector. position vector C. We're told to find position vector C. We are told this C is actually a midpoint. So C is actually a midpoint. So we are told C is a midpoint of AB. So it's actually a midpoint of AB. So the first thing to find is AB. So what we can do is that we can illustrate this on a diagram. We can do a sketch, a rough sketch of this. But once at the first question, we don't need even a sketch because the first question is asking us to find AB. To find AB. So AB is just a B minus A, right? So what was B? 3, -2, 6. That's B. Minus A, what is A? A is 1, 0, 3. So the column vector AB would be 3 minus 1 is 2, -2 minus 0 is -2, 6 minus 3 is actually 3. So that's the answer. Okay, the second question now says that we find the position vector C. We find the position vector C, which is actually the midpoint of AB. Okay, so if we do the rough sketch, we have something that looks like this. This is A, this is B, and then we have O here. That's what we have. And B, we were given B as 3, -2, 6. A, we were given as 1, 0, 3. Okay, that's what we have. And OA, that's in that direction there. And then remember, we're told that C is what? The question is said that C is the midpoint of AB. So C is the midpoint of AB. Midpoint of AB there. So OC, if I'm moving from O to C, I would put that. But what we know is that C is a midpoint of AB. That's what we have. So from here, it actually means that what would be OC if I'm finding OC? OC would be OA. OC is this going that way. Okay, this and that. That's what OC is. So OA plus AC. That's what we have. But look, we know what AC is because C is a midpoint. So we know AC. AC is actually half of what? It's half of AB. And we have already found AB, right? We found AB, which is this one here. So it's 1/2 of 2, -2, 3. Which gives us what? So you're dividing 2 throughout, guys. So that will be 1. If you divide this by 2, this will be -1. And the last one will be 3/2. 3/2. That's AC. So we can now put it back there. Okay? We can now put it back there because we know OA. We know OA. OA is just that. That's what OA is. Remember, I told you this is the distance. This is from the origin. So OA we have, AC we also have. So we can find OC. So now OC is OA, which is 103, plus AC, which is 1, -2, -1, sorry, and then 32. Which if you had, you're going to have what? 2, -1, 9/2. That's what we have. And that's the answer for OC. That's the answer for OC. Okay, so with this done, guys, so I challenge you to go and do exercise 9.3. Please go through that exercise and try all the questions that are there. Whenever you get stuck, you can reach me and then we do them together. So make sure you go through those questions. So with that said and done, I can talk now a bit about vector equation. I can talk a bit about vector equation. Now, just like you have just like you have equations of tangents in calculus where you write equation like that, or you use this formula. X minus x1. Even in vectors, we also have similar equations, because whenever you talk about a line, you can now talk about equation of that line. You can talk about equation of that line. So even in vectors, we have the concept of equations, except that here the equation we are talking about is actually written like this. It's actually written like that. B is actually a direction vector. That's what B is. It's a direction vector. And this A here is actually a position vector. So what do I mean? What I mean is that if I do a sketch, you're talking of the point here and another point there, which is B, and then you're talking of this, so moving from A to B. Okay, so you always take A is a position vector, which mostly is just a point on the line, and mostly would take this here as the position vector. So this point here will be our A. Okay, our B is going to be AB. That's your direction. You're moving from A to B. Okay, and we know how to get this from the previous class that I'm talking about. We know how to get this. This is a direction vector. The position vector will always be this starting point here. We always get that. But anyway, A is just a point on the line. So that will be the vector equation of this line here. Okay, an example would be we have we want to write a vector equation of a straight line. For the straight line through 3, 1 with direction vector. Direction vector 4, -2. That's a direction vector. So here every information is given that we need to use that and write the equation. Every information is given here. So we can just go ahead and write. This is always a position. That will be the position vector. So this will be the position vector. And this is a direction vector given there. So then the equation will be 3, 1 plus, we just write them everything in columns form. T, and then we have 4, -2, which now gives us 3, 1 plus T. Then we have 4, -2, and that is the vector equation for the straight line that we needed to, they asked us to find. Okay, so in this case, they gave us everything. What if in the case where they have not given us the direction vector and the other information we need to have? So there's this equation here which says find the we find the vector equation. We find the vector equation. So we find the vector equation for the line. For the line through 1, 2 and M 5, 3. Okay, so so here, if I do a sketch, guys, here, this is 1, 2, it's a point somewhere there, and 5, 3 is a point somewhere there. So we are talking of this line here. This is L and this is M. That's what we have if I do a sketch. And so we want to write a vector equation. That's what we want to write. I believe we're in that direction here. Okay, so this starting point here will be our A. Now remember, this is our A, which is what? 1, 2. That's our A. So which is 1, 2 plus T. This direction vector here would be LM, guys. That's a direction vector. And we know how to get this. We're just subtracting this minus that. So we're just saying 5, 3 minus 1, 2. Which gives us what? 4, 1. So this is 4, 1. And that's the equation we needed to write. That's the equation which we needed to write. Okay, so I move forward and then I talk about how to show a point is on the line. Is on the line. I have to show that. So how do we get to show that a point is on the line? Okay, which is a very good question. So I'll demonstrate this with an example. There's an example which says that we have 2 points. We have points A and B. Okay, points point A as exact. These are position vectors, 3, 1, and -4. And this one here is -2, 5, 0. Now remember, these are position vectors, both of them. They're position vectors. Okay, so now we want to write, so the first one, we want to write a vector equation. We want to write a vector equation. That's what we want to write, equation. That passes, the vector equation that passes through A and B. Want to write a vector equation that passes through A and B. So what do we do? So we're using the same equation, guys. Nothing has changed. We're using the same equation. R is equal to A plus TB. Right? A plus TB. So A plus TB. So your A is going to be the first one, which is 3, -1, 4, plus T. Okay. Your B is a direction vector, which in this case is going to be AB. Right? And meaning you're just subtracting -2, 5, 0 minus 3, 1, -4. Which gives us what? -5, 4, and then 4. So which we have here, that's a direction vector, which we have here. So we have written the equation, right? And so the second question is saying that we show that we want to show that the point C, this point is given by this -12, 13, 8. -12, 13, 8 lies on the line. Which line? The line we are from writing lies on the line. Which line are they talking about? The line which we have written. The line which we have written, which is 3, 1, -4. The previous line we just wrote, plus T, -5, 4, 4. That's the line we are talking about. So how do we show that this point lies on the line? Now, you guys, you know that, for example, before I continue, if we have a quadratic equation of this kind here, you agree with me that 1, 1 lies on the line. Why? Because if I substitute in 1 where there's x, if I substitute in 1, I'll be able to get 1 where there's y. So this point here satisfies it, right? But look, if I put in this, guys, 5, 1, Now you see, guys, this does not lie on the line. Why? Because if I put in 5 here where there's x, 5 squared is 10. It's not 1. So this point here does not lie on the line. It doesn't. So this doesn't lie on the line. It doesn't lie on the line. So that's your idea we're actually doing here. So when we say it lies on the line, what you're actually saying is that when you substitute in some x value, you're supposed to get this corresponding value of y, which in this case you don't. Okay? So what is the idea here? So the idea is that if this point lies on the line, okay, that is to say that this 3 negative, 3, that is to say that 3, 1, negative 4, plus t, negative 5, 4, 4. If that point C lies on the line, which is what C? C is negative 12, 13, 8. So if it lies on the line, all you are trying to do is that there's some t. This is a unique t. There's some t. So there's some unique t. Okay, there's some unique t. There's some unique t which gives you this. So in short, you are thinking of this as your x from the previous example that I demonstrated with a quadratic equation. So there's some x value that you substitute in to get a y value. Okay, if that x value that doesn't exist, then this does not lie on the line. So let's now try to see if we're able to find a t. If we find a t, then indeed the c lies on the line. If we do not find that t, then it doesn't lie on the line. So now remember, we are just doing this component wise. 3t times negative 5, so we have 3 minus 5t. That's the first one, 1 and 4 there. So we have 3 minus 5t is equal to equate to the first, negative 12. Then we have 1 plus 40 equate to what? 13. Then we have negative 4 plus 40 equate to what? We equate to 8. Now the value of t, remember here that you are finding, these equations must be consistent. What do I mean? You should be able to find the value of t. Okay, you should be able to find a value of t, which is actually a non-zero. Okay, it should be a non-zero in this case, non-zero. And the same value of t should satisfy all the equations. There are 3 equations here. It's the same value of t. If this is not true, then the point does not lie on the line. Okay, so the same value of t. So if we are solving this, you can solve, you guys. So t, actually you see that t is equal to 3. Even from here, you can do that. 13 is equal to 1 plus 40. You're solving for t. Okay, so you're taking this other side, which will be 12, and then 12 dividing 4, you get t is equal to 3. Now you see that this 3 satisfies all the equation. When you substitute there, you get negative 12. When you substitute here, you get 13. When you substitute here, you get 8. So t exists. So indeed, c lies on the line. Indeed, c lies on the line. Okay, there's another question that I want to demonstrate where we have been given equation R given by this 3i plus j plus k plus mu 2i minus j minus k. This is a vector equation, right? This is a vector equation, remember, except that I've not used the t there. In place of t, I've used mu, but it's the same thing. Okay, so that's some equation there. And the question is saying that we show that this line intersects intersects the x-axis. Now, if it intersects the x-axis, we need to know the x-axis in terms of vectors. According to the way they have written it, in terms of, remember, we're in 3 dimensions. They are in 3 dimensions here. Y, X, Z. So we're in 3 dimensions. That's why you have I here, you have J, you have K here. So we're in 3 dimensions. So the X in 3 dimensions would be what? Would represent it by that. 0J plus 0K, it's the x-axis. Okay, so this C is just some number, okay? Some real number in the x-axis. So if this intersects the x-axis, then there should be some mu here, which is equal to that. This is the same thing that we were dealing with, except that the C here was given in a column vector. The C here is this x-axis we are talking about. So if indeed they intersect, then we have, it means this plus J plus K plus this mu to I minus J minus K should be equal to that because they intersect. So we are able to find some mu, which gives us that. And we can find a C. If we find a C is 0, then they don't intersect. Right? Yeah. So that C should be some number. Okay, so now we are solving this. So you're just equating the I's together, the J's together, and the K's together. So equating the I's together, I have 3 here. Here I have plus 2 mu is equal to C, which is that C there. That's equation 1. I got the J's. I'm just getting the coefficients. 1 minus here I have mu negative is equal to 0, which is that one there. Then I have that coefficient, which is 1 minus mu is actually equal to 0. Okay, so from these 2 equations, guys, you can actually see that mu is equal to 1. Now, if mu is equal to 1, which you come and substitute here to get a value of C, we'll find that C is equal to 5. Okay, so you can see we found a 5 there. Okay, we found this as 1. So indeed, this intersects the x-axis because we're able to find some number in the x-axis. Okay, so that is how we get to show that indeed the line intersects the x-axis. Okay, so after doing and going through all these things, what is my challenge now to you? My challenge to you is go and try exercise. Go and try exercise 9.4. Go and try exercise 9.4. So you go and try exercise 9.4, you go through all questions there. The moment you encounter a problem, a challenge, you reach me and I'll be there for you and help you. Okay, so I want to talk about the concept of these lines we are talking about. Okay, and basically I'm talking about intersecting lines. I'm talking about intersecting lines. Now look, we have, if these lines are intersecting, okay, we have this line, if I call it A, I have that line, if I call it B. These lines here are intersecting, okay? These are intersecting at a single point. These are intersecting at a single point. They're intersecting at single point, which is this point there. So they're intersecting, okay? What if I write like this? Well, these are parallel lines. These are parallel lines. Okay, those are parallel lines. What if I write like this? I just write like that. Okay, they are coincident. The same line, that's just the same line. Okay, that's just the same line. Now, 2 lines intersect if they have 1 point in common. You can see here that they intersect because they have that single point in common. So they actually intersect. These lines are parallel. So parallel lines are actually same direction. They actually have same direction, but no common point. You can see that there's no common point. This one is on top, this one is down there. They are parallel, but they have the same dimension. Okay, so those are parallel lines. So then there are lines we call coincidents. There are lines we call coincident. So such lines have same direction. Such lines have same direction. Such lines will have same direction and infinite number of points in common. An infinite or main number of points in common. Main number of points in common. Main number of points in common. So incident lines or coincident lines are actually lines that have the same direction and they actually have same number of points in common, infinite number of points in common. Parallel lines have same direction, but no point in common, okay? That's two lines that are parallel. And then lines intersect if they have a common point, okay? And there's this word here that we use. So this word we use it for lines that do not intersect. Do not intersect. One. And then they are not parallel. Two. And actually not coincident. So it's actually opposite to what I was just talking about. Not coincident. So it's actually opposite to what I was talking about. So lines that do not intersect, they are not parallel, they are not coincident. We call them skew lines. Okay. So let's do some work on these lines that I'm talking about here. So we have two lines here. So we have two lines. We have this one here. We're given 5, 1, negative 1, plus t, 2, 1, 5. We have another line, which is given by this 13, negative 6, 2, negative 3, 4, 1. That's another line. And then we want to show that these lines intersect. Then we want to find the position vector of the point of intersection. So we want to show that they intersect. And then we also want to find the point of intersection. Yeah, if you say they intersect, where are they intersecting? That's what we want to do. So we've been given two lines here. So I'll write them. The first one is 5, 1. If they intersect, then it means that we can do this. If they intersect, it means we can do this. This is equal to that. It's more like when you're solving two equations. Okay, you solve for the point of intersection, right? So even here, we are solving for the point of intersection. Okay, that's what we want to do. So solving now for the point of intersection, because they intersect, the question is saying they intersect, we have to show that the lines intersect. So showing that they intersect is just finding a common point. Okay, so 5 plus, you just get them component wise. You get them in that way, in this way, and in that way. Okay, so 5 plus 2t is equal to 13 plus negative 3 mu, right? That's what we have. Then we have 1 plus t is equal to negative 6 plus 4 mu. The last equation is negative 1 plus 5t is equal to what? 2 plus mu. And then we are solving. So we are solving. So we have to solve two of the equations. So we have this equation that equation, and that equation. So we can solve two of the equations to find pairs of values which satisfy those two equations. That's what we can do. So so maybe from here, I can make mu the substitute formula, and then I substitute in the other two equations. So from equation one, so in short, what I'm saying is we have two equations here. You can choose to make this mu the substitute the formula. Then when you do that, you come and substitute here and substitute there, you end up with two equations. Okay, so I'm telling you the criteria on how to solve this. I like people practicing. So since there are three equations, the whole idea is you just come up with two equations from these three. How can you do that? So you can either Q the first equation, which is equation one. You make T the subject to the formula in equation one. After you make T the subject to the formula, you come and substitute that T in equation two and also in equation three. So that you just end up with equation two and equation three that you solve simultaneously. And then you find the values of T and the values of mu. I hope that's clear. So that's actually a task I'm giving you guys. And then after you do that, you should confirm that you're going to find your value of T as 1 and the value of mu as, find the value of mu actually as 4. I mean, sorry, 2. That's what I found. So if you find your values of, you find your value of T as 1, you find the value of mu as 2. So after you do that, now we can write, and then these values, guys, should be able to satisfy all the equations. This T should be able to satisfy that first equation, the second equation, and the last equation. Not for each equation you have a value of T, no. Not for each equation you have a value of mu, no. That means they do not intersect. If they intersect, the value of T should be the same for equation 1, equation 2, and equation 3. The value of mu should be the same for equation 1, for equation 2, and equation 3. And then after we do that, we can now find the point of intersection. We can now find the point of intersection or the position vector. We can now find the point of intersection. How do we do that? Because we have found already the value of T and the value of mu. So we can use one of the two equations to find what we are looking for. We have this, remember these two lines were given. So we can use any of the two. We can use any of the two. Sorry, this is mu here. -3, 4, 1. So we can either use this one or we can use this because we have the values we are looking for. So if I'm using this one here, our 5, 1, -1 plus T is 1. So this will just be 2, 1, and 5, guys. And so we just end up with 5 plus 2 is 7. 1 plus 1 is 2. -1 plus 5 is 4. So this is the point of intersection, or that's it. That is a position vector. So that's how we find it. Okay, so if that is done, I'll move and I'll talk about how you determine whether the following pairs of, whether if they do not intersect, we determine whether they are parallel or they are not, which we actually, basically we know because if they do not intersect, like I said, you even have, even those values of T and the values of mu we found to be different for each equation. Okay, you may not find a common T or a common mu. That means they do not intersect. So we have this equation here, 452 plus t 2 negative 1 3. Okay, and then we have another equation which is r is equal to 504 plus mu negative 4 to negative 6. That's what we have. So first of all, guys, let me talk a little bit about how to identify parallel lines. Now, parallel lines, sometimes by inspection, you use the direction vectors. Now, the direction vectors, remember, this is a direction vector. This is a direction vector. Remember the equation we're writing as this. This, we said, is a direction vector. The other one is just a position vector. So you can use the direction vector to be able to identify if lines are parallel or not. Okay, so for example, like here, the direction vector is 2, negative 1, 3. Here, the direction vector is negative 4, 2, and negative 6. Okay, and remember what I said about parallel vectors? Vectors are said to be parallel if they're just multiples of each other. So you actually realize that this is just this vector multiplying by negative 2. You actually realize that. So you can see that these guys are parallel. They're just multiples of each other. So these are actually parallel. Okay. If they're not parallel, you can see that they wouldn't have been multiples of each other. Okay. They wouldn't have been multiples of each other. But if they're not parallel, you can tell they're not parallel. If they're not intersecting, you can tell that they're not intersecting. Yeah, meaning they'll have so many values of t and so many values of mu, right? Yeah. So that's how you get to tell these things, guys. Let me talk about what we call scalar products of vectors. This is just multiplication of vectors. Okay. What we are dealing with in most of the questions is adding vectors and subtracting vectors. But here we just want to talk about multiplying vectors. Okay. So if we have two vectors, mostly we have maybe the vectors are positioned at a particular angle. This is an angle here. So multiplication of these two vectors here. Okay. Multiplication of those two vectors there, inconsiderate of their directions. Multiplication of those two vectors here would be, you get a magnitude of A, we talked about the magnitude of A, times the magnitude of B, and then cos theta, the angle given there. So maybe if we had 2 here, and then, okay, let me just say A, B here, and this was 30 degrees. So A times B would be A magnitude B, and then cos 30. And then that would be the answer. Now you see sometimes, it's not convenient to always work out the multiplication of these vectors using an angle. Okay, so because of an angle, sometimes we don't go that way. Okay, we don't go that way because of an angle. So multiplication of these two vectors here, actually, like I said, is this. That's what we have. But remember, this could be, this vector could be, maybe you have A1, could be A1 plus A2 plus A3. This maybe could also be B1 plus B2 plus B3. Let's say we're in 3 dimensions, right? So instead of going this way, it becomes complicated because for you to be able to continue finding angles and angles and angles, you may not manage to find an angle because you don't know an angle that is in between them, especially if the angle is not given. So going this way seems to be a little bit complicated. So all you do is you just multiply this, you multiply by that, A1 multiplied by B1, this multiplied by that, and this multiplied by that. That means you have gotten the scalar product. Okay, that means you have gotten the scalar product. What do I mean? What I mean is, suppose you have vectors OA, that's a vector given in a column form like that. 3, negative 1, 2. You have OB given also in a column form. Then you want to find this. So you see, like I said, it's not easy to get an angle in between them. So that becomes a little bit more complicated. That's why the formula that I just talked about is easy, because all you do is you multiply that and that. Of course, you have plus, then you multiply this and this, plus, then you multiply this and that, right? And you get your final answer as 12. So that will be the scalar product. Okay, that will be the scalar product of those. So that's how you get the scalar product. Okay, but we have a particular way of how we get the angle as well. Remember, we are multiplying two vectors and we said it's the same as this. And I said that this, if you don't want to do it, or you're not given an angle, is the same as this. Especially, let's say, if we are given in 3 dimensions, right? I said it's the same as that. Okay, so it's like from here. Okay, how do we get an angle? Well, remember, guys, look, if we have these two equations here, how do we make cos theta a subjective formula? We just divide both sides by that magnitude, right? We divide both sides by the magnitude. We divide both sides by the magnitude. That's what we do. So we divide both sides by the magnitude. So we just have, cos theta is equal to, cos theta is equal to this AB dividing what? The magnitude. That's what we have, which is, remember the magnitude I said is also the same as that, right? Maybe we're dealing in 2 dimensions, so I'll end on 2 there, right? Which would be the same as that magnitude there. I've ended on 2 because I'm thinking if we're in 2 dimensions. So it would be like that. So that would be how we find the angle cos theta. Okay, that's how we find the angle. So this is, let's say we have been given 2 vectors, 1, negative 1, and 1, 2, 2, 1, 4. So we have that. Two, 1, 4. Those are 2 vectors given. And then let's say they're asking us to find cos theta. But look at the question. So we have to get the scalar product of these first of all. The scalar product, this times that, negative 1 times 2, plus negative 1 times 1, plus what? 1 times 4, over the magnitude of this. You forgot, I'm sure you remember the magnitude. It's 1 squared plus that squared plus that squared, right? Which will be root 3, right? You're multiplying by here 2 squared, which is 4, plus 1 squared plus 4 squared, right? Which will be root 21. And then we end up with what? We actually end up with, on top, if you add those, you actually get, you get 5. That's what you're going to have. Then down, if you multiply root 3 times root 21, and then you get an angle, guys. So you have cos theta here. So meaning theta is going to be cos inverse of this, right? Yeah, and then you actually get your final answer as 51.0 degrees. This is to one decimal place. So that's what we have. That's on how we get the what? On how we get the angle between the two given vectors. Okay. Now remember, if you multiply two vectors, the scalar product, if you get 0, it actually means that A is perpendicular to B. This symbol is perpendicular. It actually means it's perpendicular to B. What does that mean? So it actually means that the angle between them is 90 degrees. So that's how you know that they are perpendicular. Okay, that's how you know that they are perpendicular. So don't forget that. You should always know that when you multiply two vectors, then you get of course here we're talking about scalar product, and you get 0, and it means they are perpendicular, and that just means that the angle is 90 degrees, right? That's what it means by perpendicular. Okay, so and in the last class, I think I want to talk about finding the distance. The distance from a point to a line. From a point to a line. Distance from a point to a line. So what do I mean here? What I mean is, let's have this. This is a line, right? This is a line. So maybe I have that as A, and I have this as Q, and then I have this point here, P. So this is a line, I'll call it L. I'll call it L. Now this is 90 degrees. That's 90 degrees. So you can see Q is actually a foot of the perpendicular from the point P. This is a point. You can see that this is perpendicular to that. So this Q is like a leg or a foot, okay, of that point P to the line L, right? And remember, if we are finding the equation of the line, how do we write the equation of the line? It's A plus TB. That's what we have, A plus TB. This is B, we are talking about the direction, and A is any point on the line, right? A is any point on the line. So what we want to find is actually a distance from a point, which is this P, to that line there, which is this line here. So we want to find a distance from a point to that line there. That's what we want to talk about here. So I'm going to demonstrate it with an example. I'm going to demonstrate it with an example. So demonstrating with an example, we are told the question says find the distance. Find the distance of the point 3, 3, 1 for the line, -4, 3, 0 plus t, 1, 2, negative 4. Okay, so we have been given a point and a line. Okay, so we can think of it like the way I did the sketch. We had this case here. So this is 90 degrees. This is my Q. I'll think of it as that's my Q. So the point P we are talking about is this. 3, 3, 1. Okay, so this is a line here, right? I have this distance here, the D, which, so I have that. So now any point on the line, say Q, any point on this line here, say Q, whether Q or A, any point on that line, okay, as that position vector, which is given to us. So as the position vector, remember how we are solving for the position vector in the case of intersecting. We are solving for the values of t, and then we substitute back and get the position vector or the point of intersection. So any point on the line, say Q, will have this equation here. So any point I'm representing will have this position vector. Negative 4 plus T1 right plus T3 plus 2T 0 minus 40. Now, don't forget, guys, you can also see that the position vector here is what? I mean, the direction vector here is what? 1, 2, negative 4. That's a direction vector. Okay, so we know that any point on this line here, L, will have this position vector. Okay, and then we also know that that's a direction vector there. That's a direction vector, 1, 2, negative 4. Now, for Q, you can see that Q is perpendicular. Q is perpendicular from P to the line, right? Q is perpendicular. This is P here. This is P, the Q is there. So Q, you can see this line here. So Q is actually a foot, okay? Because a foot of the perpendicular from P to the line L. This is P here. So this is L here, right? So if so if this PQ, guys, this one here, PQ, remember, if they are perpendicular, it means they give us 0, right? This PQ here, multiplying by the direction vector, 1, 2, negative 4, should give us 0, guys. Because they are perpendicular, so they should give us 0. But what is PQ? PQ, we know how to get PQ. PQ is actually Q minus P, right? PQ is Q minus P. That's what PQ is. It's Q minus P. But what is Q? Q is actually a position vector, we said, which is negative 4 plus T, then 3 plus 2T, then 0 minus 40. This multiplied by what? I mean minus, sorry. This, we're subtracting what? P. What is P? P is given as 3, 3, 1. That's what we have. And so we're going to have 7 plus T, 2T, and then negative 40 minus 1. That's what we have. So this is PQ that we are multiplying by what? By the direction vector. And we expect that to give us 0, right? So I'm going to do the multiplication and we expect that to give us 0. So we were multiplying, we have found PQ. We have found PQ, guys. We have found this PQ, which is this. And we are multiplying by what? We are multiplying by that direction vector, 1, negative 2, negative 4, and we expect to get what? 0. So if we multiply that, what we are solving for is the value of T. We need to know the T. So we have this times 1, right? We have negative 7 plus t, which you are multiplying by 1, nothing changes, and then plus 2t times 2, right? So 2t times 2, which is 4t, right? Plus negative this times negative 4, right? Which is negative 4t minus 1 times 4, and this should give us 0. Okay, now when you solve this equation here, guys, you actually find that your t is equal to 1/7. That's what you're going to find, solving the equation. Now, after we found the t, we can now go ahead and find the answer, because all we needed to find is a t. That's what we needed to find. What we needed to find is a t, because the distance we are finding, guys, is actually PQ. The distance we're interested in finding is PQ. Because remember the sketch I did, which was like this. This was P and Q. So the distance we are just interested in finding is this. But we cannot go ahead and find that distance because we don't know T yet. So that's why we needed to T. So everything we've done here is to find the T. So now that we know T, we can now go and find what we want to find. So PQ. So PQ now is what? Is now, remember we're just substituting on PQ. PQ is this. So we're just substituting that on the T part, and then we subtract. That's what we are doing. So we just substitute, we have found the T, so we're substituting T there, and then we subtract. That will be our PQ, which is actually going to be, negative 48/7, 2/7, negative 11/7. That will be the PQ. And then after finding that, our interest is to find the distance. Now remember, distance is magnitude. That's what distance is. Distance is magnitude. So then it means the PQ is what? The PQ will be 1/7. I can factor out 1/7. You can see there. 1/7. And then I get negative 48 squared. Remember, it's magnitude. Remember, it's magnitude. Plus 2 squared plus negative 11 squared. If you never wanted to factor out, you can square each of them inside. There's no problem. Negative 48/7 squared plus 2/7 squared. There's no problem. You can also do that. Plus negative 11/7 squared. You can do that. There's no problem. Okay. I just found it right to take 7 outside. And so from there, you actually realize that the distance or the magnitude you're talking about is 2429/7. That's all we needed to find. Okay, that's all we needed to find. So that's a distance. So that is finding the distance between a point and a line. So you need first of all to be able to find the coordinates of the foot. Find the coordinates of the foot or the perpendicular from the point to the line. Then after you do that, you can now go and find the distance. Thank you so much for your time. Please go through this and enjoy your holiday.